Okay, so last time we were talking about peer-to-peer systems. If you remember, I introduced several different architectures for peer-to-peer systems. They were fall into two categories, what are called structured P2P systems, where the key that you're searching for maps onto a specific node within the peer-to-peer network. That node is responsible for figuring out who has the content. It could be any other arbitrary node of that node itself. Okay? So in structured P2P systems, whenever you look for an object, okay, you're trying to do a lookup on an object, it goes to a specific node that is determined by the structure of the P2P network. And then as opposed to this, we also saw unstructured P2P networks where there is no real network topology structure associated with the peer-to-peer network. So if you need to look up an object, you basically send that query, flood it through the network. It propagates to every node in the network subject to a maximum hop count, and then you wait for the replies and you get the node, get the content from the node that has replied saying it does have it. Okay? So those were two architectures for P2P network. There's one additional detail that we couldn't cover last time that I'm going to talk about, which is this notion of super peers. Okay? So what is shown in the figure here is an arbitrary peer-to-peer network. The nodes just represents peers that are participating in the network. Okay? Now, in certain types of P2P networks, what you could do rather than flooding the network, okay, if it's unstructured, rather than just simply flooding it, what can happen is groups of peers can come together, as is shown in these groups here, and they can elect one of their peers as a super peer, and that peer is designated to answer all the queries on behalf of nodes within that group. Okay, so if you say, do you have object I, if that comes to this group, rather than flooding it within the group, it only goes to the super peer. The super peer keeps track of whatever objects the peers themselves have, and it can reply to queries. Okay? And the idea is, if you choose a super peers as nodes that have more resources or have better network connectivity or more bandwidth, you're offloading some of the burden from the peers, and this super peer may have more resources than the others, and it is more capable of answering these queries. Okay, so basically, super peer nodes become more distinguished than their peers. This is not completely client-server architecture, but so think of a super peer as acting as a server on behalf of other nodes in its group. Okay? So it has some more responsibility, and it basically donates more resources than the others. Okay? So that's a peer-to-peer architecture, which is a hybrid, where rather than treating all nodes equally, groups of nodes come and elect a node to be a super peer. Okay? Now, which node becomes super peer has to be dynamic. You cannot statically assign this responsibility. It will depend on how you decide who has what resources and who should be elected. The super peer, like any other peer, can leave the network at any time, in which case that group has to elect a different super peer. So the dynamics of the network are still going to hold, and you have to make this decision online and be willing to change it if the super peer leaves or decides it doesn't want to be super peer anymore. Now, an example of this topology is used in Skype, because Skype has this notion of super peers. So what, as I had mentioned last time, Skype uses a P2P topology where peers can collaborate with one another to figure out who is logged into the network and what IP address they are. So you have a username for your Skype account. So when you log in, you have an IP address. If somebody is trying to call you, they need to know where to reach you. Okay, because your IP address is not going to be the same whether you are, let's say, in the department at UMass or you go home, your IP address keeps changing. So Skype needs to keep track of where you are in terms of your IP address at any given point in time. So if someone tries to call you, the call has to be sent to the right machine. Okay? And that is done through the peer-to-peer network. So associated with an account is where what your current status is, are you online, offline, and so on. And if you're online, what IP address should belong to. So that's a directory, okay, directory of all Skype users, okay, and whether what is their current status, are they logged in, and if so, where they are. This directory itself is maintained in a P2P fashion. Okay, so the lookup here would be the lookup for a name saying, is this user, what is the status of this user. Okay, so this directory is distributed, and peers are responsible for answering queries. But rather than each peer trying to do this, what Skype does is use a super peer architecture where a group of nodes will elect one node as a super peer, and that node is delegated responsibility for answering the queries about the status of other peers in its group. Okay, so that's how Skype would do it. So basically, now how this is determined is based on the Skype's protocol for electing super peer. But you may see that if you leave your Skype client running and you are on a good network, occasionally you may see that your machine is receiving more traffic than anything you are generating, and this is because your Skype client may have been elected to be a super peer for some short period of time. So when any other Skype client makes queries for other peers in your group, your client will have to answer those queries. So it's not just a simple client for your needs; it can also be a super peer. Yes, question there.
So something I don't understand is that Skype is a point-to-point application. Right?
Yes.
So I don't see how it's a peer-to-peer. Do clients forward traffic from other users?
Okay, that's a good question. The question is as follows. Skype is a point-to-point application where one Skype client calls another Skype client. So where does this peer-to-peer architecture fit in? That's your question, right? So there are two parts to it in Skype. One is actually making the call from one client to another. That is going to be always point-to-point. Okay? The other part of Skype is actually figuring out which users are currently logged in, what is their current IP address, and so on. That is like a telephone directory, right? So the maintenance of that directory is done in a peer-to-peer fashion. So once you figure out that your friend is actually online and you want to make a call, you'll just get their IP address. Let's say this is you and that's your friend. You'll get their IP address and you'll just directly call them. That part, the actual call or the messages don't go over a peer-to-peer network. This is simply looking up the status, maintaining who are the users, what accounts they have, what their usernames are. You can also go and search in Skype for any user. That entire directory is maintained in a P2P fashion. Okay, so you have to distinguish between actually making the Skype calls versus just looking for status of users. Okay, yes.
What's the advantage of maintaining the directory in a P2P fashion? Like you could have a simple client-server architecture where you just saved all the data in one place.
Okay. Question is, what is the advantage of using peer-to-peer? Why not use client-server? Okay. That's an architectural choice. Okay, so if Skype could have set up their own servers where they could have maintained this directory, okay, now then they pay for the servers. Okay, they have to actually pay for the servers and maintain the directory. Here you are leveraging all client resources. We give you the application for free, but occasionally we are going to make you super peer and you have to donate a little more resources to answering some queries. So now, in this case, Skype, the company which now is Microsoft, doesn't have to put up its own servers. You are actually delegating that responsibility to the nodes in your network. Okay, so that's always a architectural choice, whether you use clients or you could certainly have just said, why do all this? Let's have a centralized set of servers that will maintain it all. That's a viable architecture as well. But they chose not to do it. Okay, any other questions? Yeah.
So if I leave the department and go back to the home, so I change the network, how can I tell the super peer of my home network that I'm in this network?
Okay, so question is, if you actually change your IP address, how will you tell the super peer and so on? Right? So there is a Skype protocol that will say when you log in, you rejoin the P2P network, or if your IP address change, you rejoin your network. Maybe you are placed in that same group, you are placed in a different group, but whatever group you are placed in, you are basically going to actually tell that super peer saying, now I am user X, this is my new IP address. That is handled by the Skype protocol. You don't do anything. That's built into the Skype client. Okay? So if you go from here, you're temporarily, let's say you disconnect from this Wi-Fi network, you go somewhere else, coffee shop or home, you log in again, you have new IP address. At that point, the Skype client will figure that out and it will rejoin the network. Whether it's assigned to the same super peer or a different one is depend on the protocol, but that's not material. What is important is it will tell the super peer these are my new coordinates, and that's it. Okay, so that's built into the protocol. The protocol is proprietary. We don't actually know what exactly all it does, but we do know that it uses this type of an architecture. Okay, all right. So that's the notion of super peer, and we will move on to some other architectures that we couldn't actually talk about last time as well. So we've done client server, we've done P2P. Okay, what we'll now look at is what a different model called a client proxy server architecture. Okay, this is also referred to as edge server systems. Okay, and there's a picture here that is a little bit more confusing than it needs to be. So what the picture shows is there are these clients, okay, which are shown there at the top, and then there's a gray box here called a server. Okay? So in the normal client server architectures, clients will directly connect to the server. The server will answer whatever requests they are sending, and that's it. Okay? Now sometimes what may happen is the server may get overloaded if there are lots of clients. Okay? So if there is lots of requests coming in, one server may not be able to answer all of those requests. So in that case, you have two options. One is you add more servers. This is what we talked about when we were discussing the multi-tier architecture. Okay, the other option is you add what are called edge servers, okay, which are shown in this picture here. Okay. So edge servers are also called proxies, okay, or proxy servers. So proxy server is like a server, but it has smaller set of responsibility. A proxy server may simply cache data that's on the main server. Okay, so in this case, the client is not going to go to the main server. The client is actually going to go to the nearest edge server and send the request there. If the requested item is already cached there, then you are done. You're going to fetch it from your closest edge server. And if you do not have it at your nearby edge server, you can go to your remote main server and fetch the object. Okay? So this architecture is referred to as a client proxy server architecture. There are proxies or proxy servers that sit between the original servers and the clients. Okay? I will come back to this architecture later on in this course when we talk about web systems and so on. It's a popular architecture for building web caches for content distribution networks and so on. Okay? And the idea is there will be lots of these edge servers. So there will be servers that are fairly close to you. Okay? So if you happen to go to a nearby server and fetch the content, you are going to get much better response time than going to a far off server because it takes more time to send your request there. Okay? So you'll get better performance, and then you'll also reduce the load on the main server because some of the requests are now being handled by the edge server. The main server never sees them. Okay? So you will basically get some scalability benefits of the main server. Clients will see better response times and so on. Okay? So this is a hybrid architecture that basically introduces an additional element between the client and the server. It's often referred to as client proxy server architectures. Okay? We are only having an architectural discussion here. We will come back and see how to do this properly in the context of the web and certain other kinds of systems. Okay? But just keep this in mind for now. Any questions here? Okay. Proxies can be used for more than caching. Okay? Just keep that in mind. I just gave an example of a caching architecture, but you can use it for a variety of other things that you can offload from your main server to proxy servers. Okay. One last slide here, which is on collaborative distributed systems. An example of collaborative distribution system is BitTorrent, which you probably have heard of. Okay. So the main idea in collaborative distributed systems is that nodes are going to collaborate with one another, provide resources for other nodes to consume. Okay, so it's a collaborative environment where each node can contribute some resources to the overall system. Okay. Now P2P systems are often collaborative in nature because each peer is using resources at other peers to answer queries and so on. So that's an example of a collaborative system, but there are others. Now we are going to look at BitTorrent as an example of a collaborative distributed system. First, I'm going to explain a little bit of what BitTorrent is. You may have heard it or used it, but well, how it works you probably may not know. So we are going to go through that, and then we will see how the collaborative part comes into play. Okay? So BitTorrent is a distributed system that is designed for downloading very large files. Okay? So these could be files that are, if you have software distributions or DVD images of new software, let's say it's operating system software comes out, rather than going to one site and downloading a 4 gigabyte download image, what happens in BitTorrent is this large piece of content is partitioned into smaller pieces, These pieces are then distributed to multiple nodes. And then when you need to download it, you can connect to multiple nodes and download each small piece in parallel. So it basically parallelizes the download rather than sequentially downloading a large file, which may take hours. If downloading, let's say, a large several gigabyte data set or an image may take a very long period of time. So if you parallelize it, you may actually be able to download it faster. That's number one. Number two is it also distributes the load of downloads across multiple peers in the system. Okay. Now that's the basic idea. How it works is actually shown in this picture here. Okay, so first, in order to download any object in BitTorrent, you have to get what is called a torrent file. Okay. A torrent file will have information about who is storing all of the content and so on. Okay. And this torrent file you can get from a web page or whatever forum that says, okay, new Linux distribution came out, new version of Ubuntu came out, here's a torrent file to go download it from BitTorrent or something like that. So somebody is going to post this torrent file for you. So here you just have it posted on some website. Okay? So you have to figure out how to get the torrent file. But let's say you get the torrent, and then what a torrent file has is it has information about how to get the content. Okay? So in particular, it will have a pointer to what is called a tracker node. Okay? A tracker node is actually going to keep track of which other peers in the system actually have pieces of the content for this file. Okay? So you have, let's say, a 4 gigabyte file. You partition it into 100 megabyte chunks. Okay, so there are lots of chunks. These chunks are distributed. Now each chunk, there may be multiple peers who have a copy of this chunk. Okay, not that there's only going to be one node each. So you will have to have a tracker that says, okay, where is chunk 1? Here are 3 peers that have chunk 1. Where is chunk 2? Here are 7 peers that seem to have chunk 2. So it's going to keep track of which peers are live at this point in time and who has which chunk. Okay, so that's a tracker node. That's what is shown here. Okay, so there may be, so that's a tracker node. A tracker node itself keeps track of which are the nodes that have the content, and those are the nodes that there are n nodes, each of which has some subset of the content. Okay, so to get to a BitTorrent file, first you have to get a torrent. The torrent will point you to the tracker. Your BitTorrent client will have to go ask the tracker, say, okay, I need to start downloading. Who should I contact? So you'll say, here are 3 possible nodes that have chunk 1. Here are 2 possible nodes that have chunk 2 and so on. So what your client will do is then set up parallel connection. It will pick one node that has the first chunk and say, okay, start downloading from there. It will pick another node that has chunk 2, it will start downloading. So it may set up some number of parallel connections. As each chunk finishes, it will then find a node that has the next chunk that is yet to be downloaded and set up a connection and start downloading. Okay? So that's how BitTorrent works. So you basically take your object, partition it into chunks. Chunks are stored with nodes. There's a tracker node that tracks who has the chunks, and then your client will perform these downloads in parallel. So far, so good. Any questions on this? Okay. So now where does the collaborative part come in? Okay, so the collaborative aspect of BitTorrent is sort of built into the protocol here. So what they do is they basically say that if you are participating in the system and downloading data from other nodes, then you have to contribute back to the system and allow other nodes to download from you. Okay? If you are going to, so you can assume that nodes are either selfish or not. So if you behave in a selfish manner which says, okay, I'm done downloading this content, I'm going to shut down my BitTorrent client because I have nothing more to do, then you're basically disconnected from the network. You're not offering the chunks you downloaded to other nodes. Okay? If you do this repeatedly, what BitTorrent will do is it will figure out that you're not volunteering your resources. So the next time you try to start downloading this, it will slow down your speed. So it will take you longer to download. In other nodes will be told not to deliver the content to you at the fastest possible speed, so you'll actually slow it down. Okay. On the other hand, if you contribute your resources to the system by allowing other nodes to download from you, then you are given an incentive saying you are helping other nodes are helping you. So next time you try to download something, I am going to increase your speed to whatever it is. Okay, so you have this incentive that is built in for collaboration. Okay, so it encourages collaboration because you realize that if you act selfish too many times, then you suffer. The next time you go to the system and say, I want some content, other nodes are providing their resources, but you are not doing your fair share, so then you suffer. But if you participate, then you get the benefit just as others do. So that's the collaborative part. Okay, so you are going to force what is called altruism, which is you need to be altruistic, not selfish, and that is built into the protocol to encourage the notion of collaboration. Okay, so you provide incentives for good behavior and disincentives for selfish behavior. Okay, so there are distributed systems that will have this kind of behavior built into their protocols to encourage other nodes to participate and so on. Yes, question.
Is the tracker highly available?
Is the tracker highly available? So there are different versions of it. You can of course ask the question, what happens if the tracker goes offline and so on. So there are variants, I believe, where you can have more than one tracker also. Okay, but I am not fully familiar with that. There is at least one tracker, otherwise you can't download anything. Okay, that tracker essentially has a directory of who is live, what chunks do they have. Okay, any other questions? Okay, so this is collaborative systems, and I believe I have one more slide and we will be done with the architecture detail. So the last architecture that I want to mention here is what are referred to as self-managing distributed systems, also referred to as autonomic distributed systems. Okay? So these are systems that are intelligent enough to sometimes make their own decisions without users telling them what to do. Okay? So they have intelligence built into them. Okay? They can use this intelligence to autonomously or make decisions without users telling them what to do. So what kinds of decisions could this be? So you have a whole class of decisions you could make. You can have what are called self-healing systems, which if nodes fail, they will heal themselves by asking other nodes to create new replicas and so on. Okay, so they can handle faults directly, automatically. Another class of systems is self-managing in terms of ensuring that every request that comes into the system is going to be serviced by having enough capacity to service the request. And here's a picture that shows you an example of how to do this for web servers, where we are going to vary the capacity allocated to the server based on demand in an automatic fashion or a self-managing fashion. Okay, so the way it is going to work is you're going to monitor the workload that is going to come to a website. Okay, let's say there's a website, it's running on some server. You're going to monitor how many requests are coming in, how many requests per second are coming in. Okay? And based on the workload that you observe, you're going to make some predictions of what is the workload going to look like in the future? What is the workload going to look like tomorrow or for the next 1 week based on what I have seen in the past week? Okay? So you're going to use some prediction model. If you see that the workload has been steadily increasing, you can predict that it may continue to do that in the future, for example. Or if the workload has been flat, you may predict that workload may remain unchanged. But whatever it is, you make a prediction. Okay? Now, based on that prediction, you then look saying if the workload is going to be X in the future, does my website have enough capacity to service that request? Okay? If not, then you are going to autonomically allocate additional capacity to your server, saying I have one server, one dual core server, I'm going to receive 100 requests per second, that's going to saturate this server. I'm not going to have enough capacity to service 100 requests per second. So I need a second server. You will allocate one on the fly. Okay? No administrator is not going to start that server. The system is going to make that decision automatically. It's going to pull an idle server from a pool and then allocate that server to service requests for this website. Okay? So this is an example where you are making capacity decisions automatically, okay, without any system administrator going and just start a second server, configure it for the website and so on. The system figures that out, it configures itself, it does all of that automatically. Just one example of what some of these systems are able to do. Okay, they can also handle failures automatically. There are many other things that they can do. Okay. So all of these systems fall under the category of autonomous systems. Okay. They have to have the ability or the intelligence to understand what's going on in the system and make decisions to handle whatever they are observing. Okay, that's the basic idea. Okay, is that clear? We'll again come back to some of these systems when we talk about web, because that's an example we'll use in this course. That's why I gave that example here. Okay, So that is what we had for architectures last time. What I'm going to do today is talk about processes and threads as a precursor to talking about more advanced topics like multiprocessor scheduling, virtualization, process migration, and so on. Okay, so our real goal is to think about how processes and threads and applications work in the context of distributed systems. Today's slide is mostly a recap of material you should sort of know from an undergraduate course in operating system. So this is going to be either a refresher for those of you who have forgotten, or if you haven't taken a course, this is going to give you a little bit of background so you can follow when we talk about, say, virtualization or process migration. You at least have the necessary background. Okay, so I'm going to talk a little bit about processes. This is really undergraduate material at this point, and then we'll talk about threads so that you have the right background for the next class. Okay. So it's first, let's say we go with processes. Okay, so you need to know certain concepts here. So one is this notion of multi-programming and how it differs from multi-processing. Okay. A multi-program system has the ability to run more than one process at any given time. Okay, so there's any operating system that can run more than one process at any given time is called a multi-program system. Clearly, any operating system that you've encountered, you start multiple applications. They run as processes. So they are by definition multi-program systems. Okay? So now we have to distinguish this from a multi-processing system. Okay, what do you think is the difference? One process broken into sequential tasks. Okay. Okay, what any other thoughts? Okay, so first thing in multi-processing system you have to realize is there are multiple processors. That's why it's called multi-processing. Okay, so multi-programmed systems don't need more than one processor. You can run on one processor or one core. Typically, a multi-processing system will have more than one processor, typically more than one core. So if you have any machine that are dual core, quad core, they're all multi-process systems. Okay? Now, clearly to make full use of multiple cores, you also need multiple processes. So all multi-process systems have to be multi-programmed by definition. Doesn't have to be, but are typically multi-program systems. That way, if you have more than one process, each process can be assigned to a core or a process and then processor, and it just runs on those cores or processors. Is that clear? A very straightforward concept here. So that's my difference between multi-programming and multi-processing. Here we are going to be more interested in multi-processing. And we'll talk about multi-process scheduling and so on, multi-processor scheduling and so on. Okay, another thing to keep in mind is all operating systems need to keep track of process state within the operating system kernel. This is done using some sort of a data structure which is often referred to as a process control block. The name is not important. What is important is what this data structure does. It keeps track of every aspect of the process state that the kernel needs to maintain, okay? Which could be what is this process doing at this point in time. Is it running on the processor? Is it doing I/O? What is its state? Okay? How many files does it have open and what are those files? What network sockets does the process have open at any given time? How much memory has been allocated to this process? Okay? What pages of RAM are currently assigned to this process, okay, as part of memory allocation? So all memory allocation information, all disk I/O and file I/O information, network I/O information, state of the process, as well as what's the user of this process, all of that is going to be tracked in this data structure. Okay? And the OS is then going to use it for process management. Some of these you can actually see from user space. You have done something like top or PS on any Unix-like machine, you will actually see some of these attributes showing up. There's a process ID, there's the owner of the process, there's the amount of RAM associated with the process, and so on. Okay, and I'm going to show you something in just a moment. But before that, I'm going to explain this notion of a process address space. Okay, process address space is how the process is essentially laid out in memory, the logical view of the process as it resides in RAM. And typically you can assume that the logical view of a process is a linear sequence of bytes associated with the process, and the process will have multiple segments Okay, the segments would basically be, there's a code segment, typically, there's a stack, and there is heap. Okay, there are many other segments, but you should at least know what these things are. Okay, in the code segment, you have the code for the process. Okay, that's loaded in RAM. Okay, this could be basically machine code, assembly instructions in machine code format. Okay, so you basically have instructions. Okay, that comes from your source code that's compiled in. The stack is going to contain all sorts of variables, okay, for the process, and you have the heap that's dynamically allocated memory. Okay, so every process you should assume has at least 3 segments. It typically has a lot more because there are shared libraries and other things that are linked into the process. But every process is going to have these segments. Okay, that's how a process is laid out, and this region is referred to as the address space of the process. Okay, this address space is going to have addresses which are logical addresses from 0 to n that will also get mapped to physical addresses. Okay, so this is the notion of an address space. Okay, and process at any given time is going to be in one of many states. Okay, so if you remember anything from undergrad OS, you'll know that a process will have a state such as new, ready, running, waiting, and terminated. When a process starts up, it starts in new state. This is when the OS is setting up memory for the process, loading the process, the source from disk into memory and so on. Okay, when it's actually running, it's typically in one of these 3 states which says, I'm ready to run, okay, but I'm not yet scheduled on the CPU, or I'm running, which means the process is actually executing on the CPU, or it's waiting doing I/O. It typically cycles between these 3 states, okay, many number of times, and then once it's done executing all of the code, it's going to make a transition to terminated and it's shut down. Okay, the process is going to go through these states over the course of its execution. Is that clear? It's not so obvious that nobody's saying anything, or this is something is wrong. But anyway, I'm going to show you processes in a system. So this is just a list of processes that run on this system, and you will see that processes have names. Okay? This is some statistics for the process that says this is the percentage of CPU it's taking. This is the number of threads that are in there, that we'll talk about threads in just a moment. And if you click here, you will see here is the amount of RAM that is associated with each of the process, and that's how much memory has been allocated to it. You will see that there are some ports that are associated with that are tracked. If you look at network, you will see some network statistics that the kernel is tracking, which is how much data has it sent, how much data has it received. Process ID is obviously that. Those are the ports, again, network sockets associated with the process. There's disk statistics here as well, which do the same thing, which says what are the processes, how much I/O have they done. It also track what are the open files and so on. Okay. All of this information that you can actually see here is tracked in this process control block data structure, okay, PCB. Okay, in Linux also you can see this. If you do top, you will see the same information. Okay, so all of that is coming from a kernel data structure that this application will query and show you. Okay, any questions here before we move on to scheduling? Is this clear? Okay. All right. So now let's talk a little bit about how processes are scheduled. Okay. We'll take a uniprocessor environment, which means there is one CPU core. Only one CPU, not multiple CPUs. Multiple CPUs we'll look at later. Okay. And then what will happen typically is, since you saw that there are lots of processes in the system, okay, if there's only one CPU, it's a given that only one of these processes can actually run on the CPU at any given point in time. There's only one CPU, so one of the processes runs. Okay. Since there are many of them that are wanting to run, each of them has to take turns to run on the CPU. Okay, they can't all run at the same time, so they take turns, and typically the CPU scheduling algorithm or the scheduler will determine how they get to run, in what order they get to run, who gets to go next. Yeah. So what will typically happen is, because you will have essentially a queue of processes that are all ready to run. That's this ready queue. Okay, you will have process A, process B, process C, process D, and so on. Okay? And then you have the CPU here. Okay? So it's a job of the CPU scheduler to look at the queue and pick one of these processes for execution, and then that process gets to go next. Okay? It's going to run for a period of time referred to as the time slice or the quantum. It's not going to get to run for as long as it wants. It's going to be given a time slice. Also referred to as a time quantum. Okay? Now, if the time slice expires, means it runs for the entire time slice, this process is going to be evicted from the CPU, saying your turn is done. Okay? It basically goes back to the end of the queue, and some other process gets to run. Okay? Now, during its time slice, the process may also decide to do some I/O. It may decide to read some data from a file and so on. If it does I/O, it also gives up the CPU. Okay? Let's say it was running and it decided to do some file I/O before its time slice expires. Okay? Even in this case, it has to give up its CPU. Okay, why? Okay, next, but why is it giving it up? Its time slice is not expired, is all I was trying to ask.
The I/O takes time. Yes.
Okay, so the I/O is going to be slow. By then, so typically I/O is slow, so if it just sits there, it is waiting for the I/O to finish, not doing anything. Okay, so I/O requires you to wait. You say, read some data from disk. Until that data comes, the process is just sitting there, not doing anything at this point. So if any process does I/O, rather than waiting on the CPU for the I/O to complete, a better option is for this process, okay, to be taken out of the CPU and put on a wait queue. A wait queue is a process that contains all processes that are waiting for their I/O to finish. Okay? Because there's no point in it sitting here and wasting CPU cycles doing nothing. So you'll evict it, you'll put it on the wait queue, CPU scheduler will run, it will pick the next process and run it. Okay? When that process's I/O finishes, it will rejoin this queue saying my I/O is done, now I'm ready to run again. And this is how any CPU scheduler would work. Next question.
At any point in time, if the process hangs, is there some way in order to in the OS itself in order to terminate that process?
Okay, question is, the process hangs, is there any way to figure this out and terminate it? Okay? There are techniques to detect certain kinds of deadlocks which also cause a process to hang. If an OS actually implements those techniques, then you can detect the deadlock and terminate the process. But by and large, most operating systems do not implement this kinds of techniques because they're too expensive to run. So if your process hangs, it's left to the user to say, you figure it out. It's your process, it hung, you can kill it, you can restart, do whatever you want. And that's the technique, I mean, that's the decision that most operating systems take. Not that they cannot do something about it, they choose not to. Okay. Any other questions here? Okay, so now having talked about a CPU scheduler, how it works, there are many different policies that you can use that will decide which of these go next and how long they get to run. And these are the policies outlined here. What I was describing in that simple example is a round robin policy. Each of the processes in this queue get to go in a round robin manner. Process 1 goes for some time, and then if it's done, it goes to the end of the queue, then process 2, process 3, and so you do round robin in that queue. A very straightforward policy. Okay, that's called round robin. Another policy here called shortest job first. So what this policy does is it looks at all the processes in the queue. It doesn't pick the one at the front. It picks the one that is the shortest length. It's taking the shortest job and it schedules it next. Okay. Now there are certain properties of a shortest job first scheduler. One of which is it is optimal in terms of waiting time. There are no other policy, or there's no other policy that can give you any less waiting time than shortest job first. Okay, so that's a reason you could potentially do shortest job first, okay, rather than just doing round robin. Okay. Anyone remember shortest job first? Yes, you have something to ask.
If there are ties among the jobs.
Okay, if you have ties, you can break ties arbitrarily. Shortest job first doesn't say anything about how ties are to be handled. It simply says, look in the queue, pick the job which is the shortest time to finish. If there are two jobs at the same identical time, you can arbitrarily break that tie. Right? There's something here. Yes.
Short in terms of what?
Okay. Short in terms of what? So that is a good point. That depends on the exact variant of shortest job. First, you could start with from the time it started, you look at the length of the job and say that's my definition of job length. Okay? Or you could say I am at this point in time, this is my shortest remaining time, which is called SRTF, shortest remaining time first is simply a variant of shortest job first. So you can just look at total time to completion from this point in time, whatever any of those metrics work, you're just defining how long it's going to take for the job to finish, either from the start or from this point in time. Okay.
And so the CPU has to calculate the job length in advance to know the job length of each job.
Yes. Yes. So I think that's a good point. The point is that in order for this policy to work, you need to know the job length. Otherwise, how do you know what's the shortest job? You will not. Okay, so this has to be known. Okay, so what does that tell you about the policy?
It's difficult to implement it really.
Okay. It's difficult to implement it. The reason is, how does the operating system know how much time this process is going to execute? You start a browser. Okay? How is the OS going to know when you're shutting it down? It has no idea what you are going to do as a user. You start your mail application. OS has no concept of how long a user can decide to run it for as long as they want. Right? So for many applications, impossible to estimate job length. For some applications, you may be possible to estimate it from start to finish because you run it over and over again. You may be able to say, based on past estimates, it runs for X amount of time. Only a guess, no guarantee. There's no way to know how the process is ever going to execute, how long it will take. Okay? So although this process scheduling algorithm is optimal in terms of waiting time, it is nearly impossible to implement in practice because it needs knowledge of job lengths, which in most cases you cannot figure out as an operating system. Okay? Good property, impossible to actually implement in practice. Okay, so that's shortest job. First, a FIFO just means first come, first serve. It does nothing but simply takes them in first come, first serve order and just run a job to completion. Okay? It's better for batch jobs or batch schedulers where you have batch of jobs. You take the first job, you run it, and you run it until it finishes. Okay? You're not doing time slicing or anything like that. Just run it to finish and take the next job, you run it to completion and whatnot. Okay? So that is first come, first serve. Okay? Lottery scheduling is a randomized scheduling algorithm. You take an algorithms, you know what randomized algorithms are. This is an example of a randomized CPU scheduler. Okay? So what it does is it runs a lottery at any given point in time. The way it works is each process is given some number of lottery tickets. You know what a lottery ticket is, right? Okay. So then each process is given some number of lottery tickets. Whenever the CPU scheduler runs to decide which process gets to go next, it takes all the lottery tickets from all of the processes, puts it in a hat, runs a lottery and picks a winning ticket. The process that holds that winning ticket gets to go next. That's completely randomized. So you can assume that each process, let's say, is given one lottery ticket. So there are 4 processes, each of them is given one lottery ticket. Okay, and then when the CPU scheduler runs, it's going to put these 4 tickets in the hat, randomly pick a winning ticket, and the one process that wins gets to go next. Okay, so if you have 4 tickets, the probability that you win the lottery is 1/4, 25%. Okay, so on an average or long periods of time, if there are only 4 processes in the system, every 4th time slot you should win the ticket. Okay, it's randomized, there's no guarantee of course, but that's what will happen. So you'll get 1/4 the CPU time, your 4 tickets. Okay, so essentially if there are n tickets in the system, okay, you will get, if you own some number, I of those tickets, the probability that you win the lottery is I over n. Okay, so by controlling the number of lottery tickets, you can also control how much CPU time each process needs. If you want to give more CPU time to certain process, you give it more tickets so that this probability of winning the lottery goes up and it will run more frequently. Okay, so this is a randomized scheduler, but it also allows you to control the amount of CPU time that a process will get. And that's lottery scheduling. Last one is called earliest deadline first, or EDF scheduler. This is a scheduling algorithm that is used for real-time systems where you run time-critical tasks. Okay, there are certain class of systems where it is important to finish a task by a certain deadline. Otherwise, something bad may happen. Okay, this is often used in mission-critical things like, let's say, the anti-lock brakes on your car. They're controlled by a tiny computer on your car. Okay, when you detect that your car is skidding, it needs for the anti-lock brakes to come on, and it needs to come on precisely on time. Otherwise, if it takes a long period of time, your car may go out of control. Okay? Computing systems that run airplanes or control nuclear reactors or manufacturing plant, all of them need to ensure that when something needs to happen, it needs to happen in a small amount, in a certain amount of time or a given deadline. So you don't use general purpose operating systems which do not give you any such guarantees. You use special versions of operating systems that are called real-time systems. These real-time systems use specialized schedulers like this one, which is called earliest deadline first. What it simply does is, if there are n tasks and each task has a deadline, you just order them in deadline order. You run the most urgent task first. That's all it is doing. But these are, and by doing so, you maximize the probability that you will actually will make the deadline and so on. So that's a specialized scheduler. It's not used in general purpose operating systems. But they're all examples of uniprocessor schedulers. Any questions here? I think we spent quite a bit of time on this. What's the difference between FIFO and round robin? That's your question? Okay. Round robin scheduler uses time slice. Okay. So you have queues, processes in a certain order. Each of them is going to give given a time slice. Let's say 100 millisecond time slice. When your time slice expires, you go to the end of the queue and repeat. So you're going to do a round robin order. FIFO, which is also called first come first serve, okay, does not have the notion of a time slice. It basically, once you pick a job, you run it to completion. Nothing else runs. That is why I said it's used for batch jobs or batch scheduling. So you pick B, you let B run. When B finishes, you pick the next one. There's no notion of time slice. It's a non-preemptive schedule. Okay, so I'm going to speed up a little bit. So here is a graph that shows you distribution. That's not quite important. So what is important is how processes behave. Okay, so typically when you take a process and look at its lifetime, you'll see that the process does some amount of computation over its lifetime and some amount of I/O. Okay, so any process is going to alternate between doing computation, which is running on the CPU, and doing I/O. Okay. Now certain processes may do a lot of computation, very little I/O. Those processes are called CPU bound or compute bound processes. Okay, they largely do computation. Other processes may largely do I/O, very little computation. Okay. These processes are called I/O bound processes. Okay. And many other processes will have a mix of computation and I/O. Okay. What this slide is simply showing is, if you want to look at process behavior in terms of how much computation they do, the length of the CPU bursts between I/O is essentially will have there will be lots of short bursts with a longer tail, because high variance in terms of long tail. There will be occasional long bursts of computation and then frequent short bursts of computation. Which means you do a little bit of I/O, little bit of computation, go off, do I/O. Some more computation, do off, do I/O. Then you may do a long burst of computation. Then you do some I/O. Then you may go back to doing some short bursts and so on. Empirically, when you observe process behavior, you will see that that is how processes behave. That they may have some small short bursts of computation and occasional long bursts of computation. And experimentally, if you actually look at this hyper exponential distribution, which is shown here, that is how CPU burst distributions look like. And so essentially, this says that what is the probability that the next time you run on the CPU, what is the length of your burst? Okay, that's the probability, that's the length of the duration of the burst. You see that there's a long tail here, okay, which is that with low probability, the next burst is going to be a long burst. And with much higher probability, which is here, it's going to be a short burst. That's all this is saying. So there's no need to dwell too much on it. So it's just a way to capture process behavior, okay, which is that the processes alternate between CPU and doing I/O. If you look at the length of CPU burst, they essentially follow a hyper-exponential distribution where most bursts are small, a few bursts are long. Okay? Why this is important, we'll come back to it when we do some other more advanced scheduling, and we'll try to take advantage of this behavior to optimize the behavior of the CPU scheduling. It's just behavior of the process at this point. Any questions on this? Okay, so that's process behavior. Then we will now talk a little bit about, I talked about 4 different scheduling algorithms. We'll talk a little bit about this notion of multi-level feedback queue, which is an example of a priority scheduler. Okay, so this is a scheduling algorithm that is often used by uniprocessor operating systems. And there's a small picture here. I'm going to draw another one here. So what happens in this case is you don't have one round-robin queue. You have multiple round-robin queues with different priority levels. So this is your CPU. Okay, so you have Q1, Q2, in this case Q3. Okay. So think of it as a generalization of round-robin, where instead of having one queue, at what I showed you here, now there are, in this case, 3 different queues. Okay. Each has a different priority level. Let's say this is the highest priority. This one is the lowest priority. Okay. So the way the CPU scheduler will work is whenever it's time to pick a process to run, it will first look at the highest priority queue. Say, is there a process there? Is the queue empty or non-empty? If the queue is non-empty, you'll just take that process and run. So you'll do round robin at the highest priority level. Once that queue becomes empty, then you go to the next priority level. And if there are jobs there, you'll do round robin at that level, and so on. At each time step when the scheduler runs, you essentially pick the highest priority non-empty queue and you do round robin at that queue. That's how the CPU scheduler is going to work. Is that clear? So essentially there are 2 concepts here. There's a priority scheduler that's prioritizing jobs. Jobs in the higher priority queue will run with higher priority or will get chosen with more preferentially than jobs at lower priority. Okay, so there's priority scheduling, and within each priority level, you're going to do round robin. Okay. Okay. So now this question.
Is there
Yes.
a chance that in the lowest priority queue, processes never run?
Okay.
Because it will be.
So I'll come to that. So the question is there a chance that at the lowest priority queue, a process will never run because there is always a higher priority queue, that's non-empty. So that's the first problem with any priority scheduler is there may be starvation in lower priority queues. Okay, if you have a high priority queue that never empties, you will never go to any lower queue to look at them. Okay, anything that's sitting there will basically just starve and never get to run. Okay, so any priority queue or rather priority scheduler will have this problem of starvation. Okay, but that's not what I was getting at, but yes, that's an important thing to keep in mind. Okay, the first question I'm going to ask is what are we going to get by this? What did we gain by introducing multiple priority levels? Why could we have not just done the simple round robin? What does this give us?
There are some important tasks that keep on waiting. So we are looking at making sure that that's done.
Okay. So the first point is with the priority queue, you can take your processes and make some of them as more important and others as less important and give more importance to the more important ones by putting them in higher priority. That's one thing you could do that you couldn't do here. Here everyone is treated equal. They're all round robin, they're all at the same level, they all get the same share of the CPU. Here processes are no longer going to be treated equally. You're in higher priority queue, will get run at higher priority with higher priority than others. Yeah, that's the first observation. And now next question is, what should the operating system put in the higher level queues versus the lower level queues? Yes.
IO bands, the highest.
Okay. So the suggestion being made is we should now try to distinguish. I'm going to rephrase what Patrick just said. We are going to distinguish between IO bound and CPU bound processes. In the previous slide, I introduced that processes could be IO bound or CPU bound. Okay. So we are going to now differentiate between the two Yes, and there are some processes that are I/O bound, some processes that are CPU bound, and furthermore, we are going to put I/O bound jobs in the higher priority queue and CPU bound jobs in the lower priority. Okay? So then you should ask why. What does this give us? Why are we going to give preferential treatment to I/O bound processes and lower priority to CPU bound processes?
Is it because IO bound is very time consuming, so they end up waiting longer? That's
Okay.
why you're wanting to like end them first. Like,
That's kind of what you said, but not exactly, but we are on the right track. So think about what an I/O bound task does and what a CPU bound task does. Okay, so I/O bound tasks are tasks that spend most of their lifetime doing I/O, very little time doing computation. CPU bound, the exact opposite. They spend most of their time running on the CPU, very little doing I/O. Okay. So now let us take a scenario where there are only two jobs. One is an I/O bound job that wants to run, and there's a CPU bound job that wants to run. Okay, so you're given choice of two jobs. And one is I/O bound, one is CPU bound. Which of the two would you pick if you had a choice? Okay, so the point is you'll pick an I/O bound task and you can ask why. So let's say you pick the CPU bound job first. Okay, you give it one time slice. It will most likely run for its whole time slice because it's CPU bound. It's not going to do any I/O, or with low probability it will do I/O. Okay, so the I/O bound task will have to wait for the entire time slice of the CPU bound task to finish before it gets to run. Until then, it will be waiting in this round robin queue. Now let's do it in the opposite order. You pick the I/O bound task. Okay? With high probability, it will run for a little while, and then before it time slice expires, it's going to go off to I/O. It's going to be evicted from the CPU. CPU becomes empty. I/O bound task, CPU bound task runs next. Now you ask which of the two scenarios have a lower wait time. The first case, the I/O bound task had to wait for the entire time slice. So its waiting time was one time slice. In the second case, the CPU bound task had to wait for a fraction of a time slice. So which one reduced wait times? The second one. Okay? So basically this observation tells you that if you favor shorter jobs, so this is an approximation of short job. We exactly did what a shortest job first scheduler would do. This is why it favors short jobs, because the long jobs are going to backlog all the small jobs. So let's finish the small job, then the long jobs can run peaceful. That's the basic idea. So you will basically always favor I/O bound jobs and run them first. So they go out and start doing their I/O, then you can run your CPU bound task. There's nobody else waiting at that point in time, other than other CPU bound tasks. So when you have a CPU scheduler, it is always preferential to give treatment to I/O bound tasks. Okay, so give them higher priority. Okay? So that also approximates shortest job first, which I said is optimal in terms of its wait times. Okay, that is why you have these multiple queues. So you are going to put your I/O bound tasks here, CPU bound tasks there. Yes.
so if shortest job first was practically implementable, it would have been better than round robin.
If the question is if you could implement it, would it be better than round robin? In terms of waiting times as your metric, it would definitely be better because it's optimal. In fact, this is an approximation of this. This is trying to do what shortest job first would do without requiring job length. You're simply observing process behavior. All you need is to know, are you CPU bound or I/O bound? You don't need to know job length, because just by calling it CPU bound, I know that you're going to have short computation, not long ones. Okay, that's all you're using. You're not actually using real job lengths. You're using behavior to infer what kinds of lengths or bursts I'm going to see. Okay? Okay, last point is, yes, your question. What is the factor that its priority? That was my last question was, who is going to tell the OS what is I/O bound and what is CPU bound? So when you start a process, you don't tell the OS, I'm starting something, I don't know, mail client, is it I/O bound? You're not going to tell the CPU anything, or the OS anything. How is the OS to figure this out? Who is I/O bound, who is CPU bound? Yes, Patrick.
Whether it finishes its time slice.
Okay. So you are not going to tell the OS anything. Okay? The OS has to figure this out. That's the first thing. Users can't be expected to tell their operating system, think of this as I/O bound or so. That doesn't work. So the OS has to determine who is I/O bound and who is CPU bound. How does it do it? it observes what the process is doing, and based on what it's doing, it's going to label them as IO bound or CPU bound. So it uses only very simple observation. Whenever a process runs for a time slice, it is simply going to ask, did you finish the time slice or did you start doing IO before the time slice finished? And it's simply going to use this observation to label a task as CPU bound or IO bound. If you finished your time slice, you are given CPU bound label. If you did not finish your time slice for any reason, you are given an IO bound label. Okay? And based on your label, you are going to be basically put in one of these queues. If you get a CPU bound label, always you go down in priority. Okay, you run for a time slice, you finish your entire time slice, you are immediately penalized by saying, okay, you go one more level down until you always go to the lowest level. Okay. On the other hand, if you start doing IO in the midst of your time slice, each time you do this, you are going to be elevated in priority level. So if you basically run, if you are here, you don't finish your time slice, you are going to put in high. So all IO bound tasks are going to rise and end up here. All CPU bound tasks are going to drop and end up at the lowest queue. And your priority scheduler is going to do what it expects you to do. You're going to run the IO bound tasks at high priority level, and they will go off to doing IO, and then you go to the lowest queue and run all your CPU bound tasks in round robin order. Okay, that is essentially what an SGF scheduler will do, but here you don't need any knowledge of job lengths. Okay, that's called multi-level feedback queue or MLFQ. That's a variant of, or not a variant, that's a basic a foundation of how Unix-like CPU schedulers work typically. They use this policy to actually run jobs in the system. Okay? Any questions here? No. So we will continue, and I'm going to introduce this notion of a thread, and then we'll quickly go through some types of threads and so on. So whatever we have seen so far is the notion of a process. Okay? A process, a traditional process, is also referred to as a single-threaded process. We are going to generalize this notion of a process and introduce what are threads. I presume all of you at least heard the term threads. We'll now look at what they are and how they work in more detail. Okay, so I'm going to go back to that address space figure I had put here. Okay, so this was your process, or let's call it address space. So this is your code segment. Okay. Don't actually need stack for now, but okay. So I'm going to make a toy process here. So we have process that has code for, let's say, 3 functions. Okay, there's a main function, there is foo, and there is bar. So typically when your process starts, typical process is going to be single threaded. So at each point you have one instruction that's being executed, and then you sequentially execute it. If you call function here, let's say foo, you're going to jump here, execute that function, return it. So that's how your typical process executes. Okay? This is a traditional process. Now you can generalize this concept of a traditional process and introduce what are called multiple threads of execution through this process. Okay? So rather than executing only one instruction at a time, each of these threads, okay, concurrently executes different instruction, different functions depending on whatever they're doing. So essentially code for this process is executed concurrently by multiple entities. Each entity we are going to call a thread. Okay, so in this particular example, your thread 1 is currently executing that statement in the main function. Okay. Thread 2 is currently executing some statement in foo. Okay. Thread 3 is currently executing some statement in bar in this particular example. Okay. So when thread 1 gets to run, it's going to continue executing whatever it's executing. Okay. When thread 2 is scheduled, same process is going to execute some other part of the process and execute that code and so on. Okay. So now we have introduced this notion of a concurrency in a process. Okay. So there are multiple streams of execution. Each stream of execution is referred to as a thread. Okay. So all threads share the same process, share the same memory. So it's not that you have 3 copies of this, each is being executed independently. There's only one address space, the threads are sharing that address space. What is, however, different is each process is going to be given its own stack. They are all going to share the heap. Anything on the heap is shared. Each process is going to have its stack. It must have its own stack, because if you are in this function here, you need your own stack that has the variables of that process and so on. Okay, so each thread is going to be given its own stack. You are going to share them. So what we have just done is we have taken this notion of a traditional process and introduced parallelism or concurrency in them. Okay, so now code of this process is executed in parallel. Each thread is executing some arbitrary portion of the process. Different threads are executing different parts of the process in concurrently. It doesn't have to be parallel, but they are at least concurrent. Is that clear, what I just said? Now, these threads are going to be scheduled exactly like processes were scheduled. Okay, so now, rather than a list of processes, here you are going to have a list of threads. And you are going to pick one thread for execution. Same concept, but except you replace processes with threads. Okay, so now, rather than having A, B, C, you may have AT1, which is thread 1 of AAT2, and you may have CT1 and so on and so forth. So you will have process and some threads. So you have to pick a thread of a process and run it on the CPU. Okay? So this is going to give you concurrency or parallelism. If you had multiple cores, okay, this is just one CPU, your core 1 and core 2, okay, you will actually get true parallelism where you may actually get this scenario where thread 1 of process A runs on core 1 and thread 2 of process A runs on core 2. So now this process is basically executing in parallel. Some parts of it are being executed on core 1, some parts of it are being executed on core 2. Okay, so if you have multi-core system, you'll get true parallelism as a result of threads. Okay, yes, question.
What's the difference of parallel and concurrency?
Okay, what's the difference between parallelism and concurrency? Okay. Concurrency is not quite parallelism. Concurrency just says that if you even have one core here, different parts are going to run, but they are not going to run exactly at the same time. They may run at different points in time, but you are getting some notion of parallelism, but it's not true parallelism. When I say parallelism, I'm actually saying that you have concurrency, but now you are having the parts of the process run at the exact same time on multiple cores, not at different points in time. Okay, so that's the distinction between. Okay, so this is just a picture here that. Oh, yes, question.
So if it's a uniprocessor, when you have, for example, a process will be having 3 to 4 threads. So one time slice gets divided amongst all the 4 threads, or it's like every individual thread?
Okay, so the question is, if you have a uniprocessor system and you have a process with, let's say, 4 threads, when this process gets a time slice, is that time slice given to only one thread, or this time slice has to be shared by multiple threads? Okay? So part of that answer is going to depend on the type of threading system which we are going to look at shortly. There will be kernel level threads and user level threads, but a default answer is, if it is the default type of threading which is kernel level threads, then when you are given a time slice, it's given to one thread of the time slice. So the kernel is now choosing this thread gets the time slice, not that this process gets a time slice and then some thread within that process shares that time slice. So the scenario you mentioned is also going to be the true in case of user level threads, which will come to in a moment. So by default, you're going to do it if your kernel level threads, you're going to assign it to a thread of a process. That thread gets the entire time slice. Okay. So now it goes without saying that if you have concurrency and parallelism, you need to use forms of synchronization, things like locks when you access shared data structure, so that if one thread is reading, you don't want other thread to go and overwrite whatever is being read at the same time, and then you will have some sort of a problem in your multi-threaded code. So whenever you have multi-threaded code, any data structure that is accessed by more than one thread has to be protected by some sort of synchronization primitives, the simplest one of which is a lock. Okay, what that means is, if variable I is shared across 2 threads, and before you access I, you have to first get a lock. So you get a lock, then you access I, then you release the lock. Okay? By getting this lock data structure ensures that only one thread can access I at any given time. So you're not going to have scenarios where a thread is reading the value of I, some other thread go and overwrote it and cause some problem. You can't have that happening. So you want consistency for shared variables. So you are going to use synchronization only for shared variables. Any variables that are private is accessed by only one thread. There is no need for locks. Okay? But any variable that is shared, you're going to have to use primitives like locks. There are semaphores, monitors. They all do the same thing. Okay, so here's the same picture that I showed you here. where you will see that these are threads. Each thread gets its own registers, its own stack, own program counter, and so on. Okay? So all threads share the same address space, but you get a copy of the stack for each thread, and you will of course get your own program counter and registers. And so that's unique to that particular thread. Okay? So that same picture as before. So you should be familiar with some form of threading, because when you implement your lab assignments, very likely you will use some multi-threaded application to implement whatever the lab requires you to do. So you will build on these concepts. If you don't know them, you will learn them. One way or another, you will know them by end of the course. Okay? So something you need to be familiar with. If you're not, you should wait for the lab to come out and then go read up on threads, because you'll probably use it in some shape or form. Okay? So we will now look at some ways to use threads in popular applications. If you go back and look at the that processes I was showing, you will see that practically every process there was multi-threaded. Okay, that's a very common way to implement code, and I'm going to show you an example. Two examples actually. I'm going to show you an example of taking a web browser and making it multi-threaded, and you'll see why there's an advantage to making it multi-threaded. Okay, so there's no picture here. Okay, fine. So if you look at what does a web browser do? Okay, a web browser may, when you specify an URL, it will go to the server. Okay, you download that HTML page. Okay? The HTML page has embedded images. It will make additional connections to the server, download all the images within the page. If your page has ads, then you will have to go to some ad server, fetch yet more images. And once all of that content is downloaded, you are going to then render the page and display it. These are all the typical tasks. And if you click on a link, whole process is going to repeat again. So you go fetch a new page, fetch the HTML, fetch the embedded image. So let's say you write this browser as a traditional process, single-threaded process. Okay? So now user specifies a URL. This process starts fetching the first form, sets up a connection with the server. HTTP connection, starts fetching the page. Okay? Page comes in. You parse the page. Let's say it has 5 images. Okay? And you single-threaded process, so you go get image 1. So you set up a connection, download image 1. You set up another connection, download image 2, image 3, and so on. Okay? At the end of all of this steps, then you have all of the content for your page. Then you will basically send it off to the rendering part of the process. You will basically say, this is how it should be laid out, displayed, this is that the image is going, you show it on the screen. This whole process may take quite a long time. Lots of steps to perform. Okay? Now let's say you make your browser multi-threaded. Okay, there are many threads available to you. Okay? So how is the browser going to work? First, when you specify a URL, you are going to hand it to the first thread saying, go download HTML. Okay? There's no parallelism yet, so you go download the page. You hand it to another thread saying, go parse the page and figure out if there are additional items I need to download. Okay, this thread is going to go parse HTML. There are 5 images. Okay? So now rather than downloading them one at a time, you will have 5 threads saying, here are 5 images, go download them in parallel. Okay? So each thread is going to set up an independent connection to the server, and all 5 images come to you in parallel. And hopefully, parallel downloads are going to be faster than sequential downloads. If your network bandwidth is not congested, you are on a reasonably fast network, parallelism is going to win. Okay? You will download 5 images much faster than downloading each one of them sequentially. Okay? So then your job is done much faster, your page loads faster and whatnot. You don't sit there waiting for the thing to download. Basically, you click, so lots of things get downloaded in parallel, it goes on displays. So now just by making your process multi-threaded, you have given better performance to your end user. Rather than sequential processing, which a single-threaded process would do, now you can do concurrent processing. It doesn't matter that you did not have more than one CPU, because network download doesn't need CPUs. It just needs you to connect to multiple servers or the same server and download multiple images at once. Okay, so you still get the benefit of parallelism. Okay, that is essentially what is being shown here. It says, you have multiple threads. There are separate threads for doing various components of your web browser. So you can set up multiple connection If you have an ad server, you can get the ad in parallel to downloading images. A lot of parallelism can help you speed up the performance of your browser. Okay? You may have a separate JavaScript engine in your browser. You may have separate threads parsing JavaScripts and doing what the JavaScript do. So you don't have to do sequential processing. That's the point to keep in mind. Okay, so by making your browser multi-threaded, we have basically sped up the process as a whole. Okay? So next time I'm going to talk a little bit about how you can use multi-threaded concepts to make a server faster as well. This is browser. So look at a web server, see how to speed that up. Just as a way to give you some sense of how threading will help you write distributed applications and optimize their performance. Okay, so we'll end it here today. We ran out of time. We'll continue it next time.